Welcome everyone to NSTA web seminars, where you can find live interactive learning at your desktop. Today's program is part of our NGSS Core Ideas series and is titled Earth Systems. Our presenter is Jill Wertheim. Ted Willard is also online with us to provide information about the standards and facilitate the Q&A. My name is Bryn Slate. I will be moderating. Jeff Lehman is online to provide technical support. And before we jump in, I just wanted to remind everyone to visit the NSTA Learning Center, which is your online portal for over 11,100 resources for science educators. And the number of resources grows every month, and almost 4,000 of those are free now. You can add resources to your My Library, and you can bundle those together in collections. And you can make your own collections. You can also access collections that have been curated by NSTA and by other teachers around a theme. So lots of great opportunities to find information there. Also encourage everybody to check out the community forums, a great place to connect with other science teachers and talk about content and pedagogical issues. We do have live support in the form of our online advisors. Feel free to reach out to them and get help finding specific resources. They love to help out. Also want to encourage everyone to check out the free tools, including the PD Plan and Portfolio tool, which can help you organize your professional learning and meet your goals. Everything is available at learningcenter.nsta.org. Now I'd like to go ahead and introduce our presenters for today. First, we'll have Ted Willard, our Director of NGSS at NSTA. And then Jill Wertheim will be here to present the main portion of our content. So I'll go ahead now and turn it over to Ted to get things started. Welcome, Ted.
Thank you, Bryn. Thanks, everyone, for being here. I'm happy to be doing this. Give you a quick little rundown of the standards. I know some of you have heard this before, but I heard it many more times than that. So here we go. The standards basically were the work of 4 organizations: the National Academies of Sciences, Achieve, the American Association for the Advancement of Science, and my favorite, NSTA. And the standards involved a 2-step process, really. We had the development of the framework for K-12 science education that came out in July 2011, and the standards themselves, and all the different elements: assessment, curricula, instruction, teacher professional development. All of that comes about and follows from what the standards themselves have. So let's take a first moment look here and look at the framework and understand pieces of it. The big lead in all of this is the framework presented 3 dimensions in science education: science and engineering practices, cross-cutting concepts, and disciplinary core ideas. We'll talk about each of those in a second. If you haven't read the framework yet, you need to go read the framework. It's really going to be helpful in understanding the whole philosophy behind the next generation science standards. And there's no really good excuse because you can get a free PDF of it from National Academies of Press. If you love to have something to curl up at night and read before you go to bed, it's a real page turner. Try get a hard copy from the NSTA Press bookstore. So the first of these 3 dimensions, scientific and engineering practices, and we had a series of web seminars last fall about these. You can go back to the archive. But these are things that students are doing as part of their scientific exploration. So it's asking questions, developing models, planning investigations, constructing explanations, engaging in argument. All of these different aspects that scientists and engineers go about and do. They do those. You then have the cross-cutting concepts. These are things that are not unique to any one discipline in science, but cut across all of those disciplines. So pattern, scale, systems, structure and function. All of these elements here are equally important in biology and chemistry and physics and geology, astronomy, all of the different science disciplines. And that takes us to the disciplinary core ideas themselves, where we have what you would expect: life science, physical science, earth and space science, and then in addition, in engineering and technology as part of the whole core ideas approach. And so we have, in our series right now, we're dealing with the earth and space science pieces, and Jill is going to be talking tonight about ESS2 Earth Systems. It's the corner of the core ideas that we'll focus on tonight. Now, each of these areas in the different disciplines breaks down further. So Earth Systems is broken down into a bunch of different chunks here, as you can see, as are physical sciences, life sciences, etc. So that's all was outlined in the framework. But let's think now and turn our attention to the standards themselves. The standards were developed by a coalition of 26 states in a process that was managed by Achieve. Here are the lead state partners highlighted out, and 41 writers from across the country. There's sort of a show of where each of those writers came from. It was a truly national effort. And the standards themselves were released in April, and at this stage we have 8 states, which represents about 20% of the students in this country now, are in states that where the NGSS are the standards that those students would be expected to work with. You can see that. We also have a slew of other states that are somewhere in their process of evaluating these. They've either polled teachers or the board has received a report on them. Something else is going on there, and more states are expected to adopt as time progresses. So we're talking about the standards. Let's take a closer look at some examples here. Here's one we have. There's a performance expectation. It really is sort of what the meat of the standards are. Develop molecular models of reactants and products to support the explanation that atoms, and therefore mass, are conserved in a chemical reaction. So if we go and we look at that, that is a statement, I'll point to this box down here in the bottom, of what students should be able to do at the end of instruction. It is not meant to indicate what is it that students do in instruction. Teachers have total freedom to make decisions about how that all comes together. But this gives them a sense of how we should go about assessing these. This performance expectation is instruction to assessment developers. We should try to move away from the type of tests we have to something that really gets into our students learning the way we want them to. But that performance expectation is a blend of these different elements. So we can see here, develop molecular models to support an explanation. That's one of the practices. We have the ideas of reactants and products, and that atoms and mass are conserved in a chemical reaction. That comes from this disciplinary core idea. And then we have mass being conserved in a chemical reaction. Also is tied into a particular cross-cutting concept here about matter is conserved because atoms are conserved in physical and chemical processes. And so these different pieces here are blended together to make the performance expectation. So with that piece of background here, I'm going to pass things on to Jill. I want to wish her a good morning because Jill is literally on the other side of the planet right now over in Thailand, which is about 6:40 in the morning. So good morning, Jill. Thank you so much for being here and sharing with us today.
Thanks, Ted. Good evening to you, all of you. As Ted said, my name is Jill Wertheim, and I'm going to be talking to you today about Earth systems in NGSS. And I want to start this off with a little apology that I planned way too much to talk about today. In my defense, I did cut about 30 slides. But really, my nickname for this topic is everything that can and has and may ever happen at, near, or below the surface of the Earth ever. So it's really quite expansive. And the way it's approached in NGSS is, in some important ways, pretty different from the way it's been approached previously. And so I really want to give you a broad overview of this whole topic in NGSS. In an effort to not race at light speed, I may not get through everything, but the slides at least will be there for you in the archive. If I am going too fast, which is possible, please let people know in the chat window and they'll be sure to slow me down. Okay, so with that, I will dive in here. So Earth and space science is divided into 3 different disciplinary core ideas in the framework. Earth's place in the universe, Earth systems, and Earth and human activity. So today we're going to focus just on Earth systems, but I will be mentioning the other 2 a lot because they really can't truly be disconnected. So the framework development team was tasked with really re-examining science. They wanted to pare down the number of standards that students were responsible for. And so they revisited what we're expecting students to learn in K through 12. And in order to do that, they came up with a set of criteria that they used to re-examine each discipline and decide what was really essential for K-12 students. So these criteria include what are ideas that have great significance, so they are organizing concepts in the discipline, ideas that have broad explanatory power, so they explain a range of phenomena around the world, ideas that are generative, so they provide students with tools so they can take what they learned and apply it to new contexts, etc. Ideas that are relevant to people's lives, so they draw on students' previous experiences or what they're likely to experience in the future. And ideas that build across K-12. So when the Earth Science team applied these criteria to Earth systems, this is what they came up with. So they broke Earth systems into 5 what they call component ideas, coded as ESS2 A through E. And each of these has a subheading of a driving question. So they include Earth material and systems, plate tectonics and large-scale systems interactions, the roles of water in Earth's surface processes, weather and climate, and biogeology. So when I look at this set of 5 component ideas, it's a little hard for me to see how all of these are building toward one coherent understanding of Earth systems. They still come across a little bit as discrete, isolated topics. And so, but when you dig into each one, a sort of coherent goal emerges. And so one of the things that I'm going to do is I'm going to share with you what I call a conceptual framework that I think each of these component ideas is building toward. And I'm going to introduce that to you and kind of, because it was helpful to me, and use that to sort of tie all of them together. So my goals for this webinar are, 1, to go through each of these 5 component ideas for Earth systems and to give you an overview of how they play out in the standards K through 12. And I want to help you see how each of these is building toward that one coherent understanding. I want to highlight some of the important ways that these goals differ from previous Earth Science standards, and these are going to be generalizations. Obviously, every state, most states have different standards. And then finally, I want to discuss a little bit about how these new goals can be addressed in the classroom to satisfy requirements of NGSS. So to start off with, the framework that I use, again, this is nothing official, this is just something that I find helpful to kind of hold in my head as I read through all of the standards. So the big understanding they're all building toward is the following. Energy from the sun and the Earth's interior drive the cycling of matter and energy through the Earth system. This cycling of matter and energy through the system has many effects. A few of them are addressed in NGSS, including cycling of water in and out of the atmosphere, the movement of rock material across the surface of the Earth and through the Earth's interior, and interactions between the solid Earth, atmosphere, water, and biota, or living things. So again, energy from the sun and Earth's interior are the drivers of this cycling, and the cycling of matter and energy through the Earth system causes cycling of water, movement of rock material across the surface and the interior, and interactions between the 4 Earth subsystems. A secondary goal of Earth systems is to bring awareness that humans depend on and influence the natural resources that result from these systems and their interactions. So as I showed you, the third disciplinary core idea focuses on the human dimension, but really one of the big changes in NGSS is that the human dimension is really filtered throughout Earth science. We'll see a lot of it in Earth systems. In addition, we also want to make sure that students are able to apply their knowledge of these ideas to, for example, carry out investigations, develop models, or construct evidence-based explanations. We also want to know that they're aware that these can be examples of stability of change, cause and effect, or how they can be used as a platform for engineering innovation. So we want to make sure that students aren't just learning the content, but they are learning the content so that they can apply it to learn about the world around them and to reflect on the broader scientific endeavor. Okay, so I started off throwing some really big ideas at you and not a lot of details, but I want to take a break for you to digest a little bit and to ask any general questions that you might have and perhaps address the questions that I have about how using a framework like this might influence your teaching of our systems and how you think using something like this might influence your teaching.
So folks, if you want, you could post some of your thoughts on Jill's 2 questions to you, and if you have some other questions you want to ask Jill, feel free to post them there too, and we'll try to get them covered. It looks like you have people pretty on board here in terms of what their understanding is. No questions at this point. And so why don't we go ahead and
excellent. Yeah.
Move forward. Oh, we have
okay,
Rain
so
here
let's
is just
move on.
Yep.
Oh. Yeah.
Folks needed a second to type here, it looks like, so we'll give them a second. And so we've got some different pieces here about talking about unifying concepts, the idea of, incorporating energy and materials, how that comes together. A lot of different pieces are coming here. People struggling with where can they make some cut from this subject area and pull some different things together. And like Dwayne's coming here, the unifying concept will certainly be the foundation from which I'll teach Earth science going forward, about how to way to connect a lot of things that are dissimilar. Great. I think you can go ahead, Jill.
Okay, great. And if we have, in the event that we have time at the end, I'm going to ask everyone to revisit this framework. And as classroom teachers, which I am not, I'm really curious to hear about how you might reframe or rephrase this framework to help your colleagues understand it. So, keep in mind that I'm going to be asking about a little bit of feedback from you about revising it. Okay, so let's dig straight into the component ideas. Just a little bit of a word about the structure here. As I said, there are 5 component ideas. I'm going to try to give you an introduction to all of them. The first couple I'm going to dig into a lot, and I'm going to do less and less detail discussion with the subsequent ones. So the first one that I chose to go into a lot of depth with is the roles of water in Earth processes. So I'll probably call this the water cycle just for ease of speaking. So the main ideas as communicated through the framework for the roles of water in Earth processes are the following. So we want students to get this big idea that water's unique physical and chemical properties enable it to play an important role in Earth system processes. This is focusing specifically on the properties of water enabling it to play this role. The second is sunlight and gravity drive the continuous cycling of water among reservoirs in the Earth and atmosphere. So this is going to sound a lot like a familiar water cycle, but note that the perspective here has shifted from what you're probably familiar with, which is that it's not so much about labeling the parts of the water cycle. It's about sunlight and gravity driving the water cycle and kind of unifying all of these different elements of this process. And finally, the movement of water and ice shapes the surface of the Earth. So that's going to sound a lot like traditional erosion deposition that you're familiar with. So how does this play out in the NGSS standards? So this is a structure I'm going to use throughout, where I show a summary of the standards from elementary school through high school on the left side. And then I have chosen a number of related concepts that students are learning about elsewhere in earth science and elsewhere in science in general that you might want to be aware of, so you can draw on them, you can build on them, build toward them, or just make connections to them. Okay, so elementary school water cycle. Students are learning just that maps show different kinds of water bodies. So this is very observational surface of the Earth. It's not till later in elementary school where they even bring in water in the atmosphere. So they're just thinking about examples of where water is stored on and near the Earth's surface in elementary school. Elsewhere in elementary school, they're thinking about human activities and how they impact water in the Earth system, so that's something you can make a connection to, and ways that moving water across the surface of the Earth and through the Earth system interacts with other parts of the Earth system. So they're starting to put together relationships. And it's not until middle school that the heart of this topic comes in. So you see that in middle school they're learning about the flows between they learned where water is stored in elementary school. Now they're learning about how water moves between those stores. They're learning about the role of energy driving that movement. They're learning about this movement shape. One of the byproducts of the movement of water through the Earth system is shaping the surface of the Earth and driving weather patterns. They're also learning about how that the properties of water enable it to store, move, and release large amounts of energy. So middle school, there's a huge amount of learning about the water cycle. And again, the perspective that you've probably seen in standards before has shifted a little bit to bring the role of energy in the water cycle more to the forefront. Also notice that in high school there are no standards for this topic. There are standards in weather and climate that are clearly the next step from the middle school model that they're developing. So you see in high school weather and climate, they're learning that a major influence of climate is ocean absorption, storage, and redistribution of energy from sunlight. So this understanding of the water cycle as a mode of transfer and transformation of energy through the Earth system is very important as they build an understanding of the role of water in the climate system. So how is NGSS different from the way the water cycle has been addressed previously? First, you might have noticed there is no water cycle before middle school, and this might be really different for a lot of you. So they're just making observations about water on the surface of the Earth and not thinking about any phase changes before middle school. Students are being prepared in elementary school to think about this complex system that's going to be thrown at them in middle school and make them aware that it should say water stores, not energy stores. In middle school, they're going to get the flows between the stores, and they're going to use energy to bring coherence to this process. So again, rather than focusing on each element of this process, they're going to add a layer and think about what's common between each of the parts of the water cycle, and that is the transfer and transformation of energy. And finally, they're going to use water's property and movement through the Earth system to make clear connections to weather and climate, plate tectonics, and erosion and deposition. So it's really difficult to tease the water cycle away from the other systems in the way that it's presented in NGSS. So how has the water cycle typically been addressed in the classroom that in ways that we hope will change? Well, this diagram should look very familiar to you. We've probably all used some version of this. And it's not that there's anything wrong with this diagram, but what NGSS is asking us to do is to move away from really labeling the parts of this process and hone in on what's really essential about that students need to know about this process. And we can see that when students come out of a traditional approach to weather and climate, using a diagram like this, they come out with a number of incorrect ideas. This includes, these are really common ideas that students have, that water moves directly from the surface of the Earth into a cloud. So this is basically, it's really common for students to take these arrows very literally. But what the byproduct is that they think that there is not water throughout the atmosphere. And you think about the water cycle in NGSS, being aware of how energy from the sun interacts with the surface of the Earth and atmosphere, and how water moves through that system. It's essential that students understand that water vapor is in the air, and that's going to prepare them to understand weather and climate. They think that water vapor condenses when it's warmed, and this can translate into they have no idea what causes condensation. Some students have a sense that temperature is associated, but it's very clear that students often are able to label this diagram, but they are not getting the relationship between energy and these processes. Students think that rain falls from a cloud when the pool of water inside the cloud gets too full. So they're just, again, not really understanding what's driving these processes. They think water only evaporates when it's boiling. I think we all know where that misconception comes from. But again, their understanding of the interaction between sunlight and the surface of the Earth it really needs more attention. And they think that clouds always form above the water body from which it evaporated. So again, the diagram is being taken very literally, but students are not being prepared enough to use what they know about the water cycle to build their understanding of the flow of matter and energy through the Earth system. So I'd like to share with you a diagram that I found that I think focuses on what the NGSS focuses on a little better. This is a primitive diagram. There are a lot of things I don't like about it, but I'm going to talk about what I do like about it. So one thing is that it shows that there is an important relationship between air temperature and water. It even mentions hot and cold, and that is different from the previous diagram. It shows the movement of air from place to place also moves water vapor. So you can see water vapor, as it evaporates, becomes part of the whole body of air, and that air with water vapor in it moves from place to place. And as it moves, the water vapor can come out of the air as rain, and when it does that, the amount of water vapor in the air changes. You have moist air, you have dry air. And these, you can start to see that this is a perspective on the water cycle that leads directly into other topics like weather and climate, like weather and erosion. Liquid water flows across the surface of the Earth from high to low. So that's implied in this movement of rain down the mountain. As I said, there are a number of things that I would like to change. I would definitely add the role of energy from the sun in warming the surface of the Earth and in initiating this process of evaporation. I'd also make it much more clear that air temperature decreases with distance from sea level, rather than just imply that the mountain itself is cold and that's what's causing the condensation. But the point is really that NGSS is asking us to really use the same substance, but to shift our perspective in how we present it to students and really hone in on the essential basic relationships that can prepare students to think about and reason about the Earth system in a generative way. So how can we bring these concepts into activities in the classroom? So this is actually an animated data visualization that is just too big to play through Blackboard, but the link is below if you want to copy and paste it into your browser and watch it. I'm going to, in the interest of saving time, not do that here. But visualizations like this can be very useful in engaging students with the very basic concepts that they're learning, so the relationship between sunlight and surface of the Earth and atmosphere and water on the surface and the atmosphere. And using just those basic concepts, excuse me, they can start to apply it to the real world and look at a data visualization like this that shows water vapor in the atmosphere moving from place to place. If you watch it animated, it's very important if you use something like this, to make sure students know what they're looking at. So I'm sort of glossing over the introduction to what you're seeing here, which is the water vapor is depicted in this light blue, and the density of water vapor is indicated in the density of that light blue. And if you watch the animation, it becomes much more clear. This is data about water vapor across the surface of the Earth collected in 2005, shown from June through November in the animation. Looking at this can engage students in questions about, well, now they know how water vapor gets to the atmosphere, and you can see that, well, it isn't the same, there isn't the same amount everywhere. Where is there more? Where is there less? Their understanding of sunlight, energy, and air temperature can help them start to reason about, well, why is there more in some places than others? Where is it moving? What is it like in those places where there's more in the atmosphere? What is it like in places where there's less in the atmosphere? Where is it moving from? Where is it moving to? What is it like in those places? You can bring in climate change and how might these patterns change as the atmospheric circulation changes, or as air temperature changes, or any of these basic components of the water cycle are altered. What will it be like in each of these different places when that happens? So you can engage students in asking questions, in planning investigations, analyzing data, engaging in arguments. And we can ask them to reflect on the cross-cutting concepts like patterns, cause and effect, energy, and matter. We can also have students compare data from two different aspects of the water cycle and focus on one region. Again, this is an animation that you can access from the link below. You can have them compare these two different data sets in one region and develop models for where is water vapor in the atmosphere most dense, where is the intensity of precipitation. What do they know about relationship between energy, temperature, and each of these phenomena? They can use this basic understanding to look at real data and start to perform rudimentary analyses, etc. We can also bring in the human dimension. So you can use, again, these very basic sets of relationships and start asking about the role that humans play, and look at places that they're very familiar with, and think about how does the water cycle interact with people and places? and how might change, as they think about changes in temperature, changes in the amount of water vapor in different places, water vapor moving from place to place, can start to think about how that might interact with human dimension. So I've thrown a very quick overview of the role of water in our system at you. And again, a lot of the substance of this topic is the same as you've seen before, but we're just looking at it from a slightly different perspective, and it's enabling us to bring some coherence to this topic and start to move toward this unifying conceptual framework of how energy and matter cycles through the Earth system and how these systems interact with each other. So I'm going to take a minute to allow you to reflect on what I just presented, ask any questions that you might have, and possibly to answer a question I have about how these standards for the grade level you are focusing on differ from the standards that you were using in previous.
All right. Well, thanks, Jill. I see that folks are jumping in on that scale there and putting their marks up. If you are on a tablet or smartphone, remember that your markup won't work. So just go ahead and type into the chat. Let us know if you agree or disagree with that statement. And do please go ahead and type your questions into the chat for Jill, and we'll check those out and see if we can answer some of those now. But great. Thanks, everybody, for putting your feedback up onto the screen. It looks like most people are heading towards that agree side.
Great, and while people are still filling in that in, feel free to continue to do that. I'll throw a question to Jill, although I don't, since you weren't on the standards writing committee, but you're welcome to sort of throw out your own thoughts if you want to, or punt. Rachel asks, why was the water cycle taken out of the K-5 standards? Won't that give students more opportunities to form their own misconceptions?
Well, yes, I can share my own opinion, but not the word of the committee. I expect that they felt that in order to build a functioning model of the water cycle, students really need to know what these words mean, these phase changes, and that they felt that that students in the elementary school were not prepared to understand the actual processes that drive the water cycle, and so that it made sense to wait until they had enough physics and chemistry background to make sense of those processes. But that's just my guess.
Oh, great. Thanks very much. You mentioned here, Luana here has a question on your slide. You have the role of water on plate tectonics. Could you explain the connection here?
Well, that was a great catch. So they included something that I've never seen in standards before, and that I fully expect that most people will ignore because it's really, I'm very surprised that they have it. So the role of water in plate tectonics, where I see it coming in is in subduction zones. And so what they refer to is that where a plate subducts, and the subducting plate basically, the water that's kind of squeezed out of the plate as it subducts seeps into the mantle above the subducting plate, and it lowers the melting temperature of the mantle there. And that's what causes volcanism. And so they bring it in to refer to water as lowering the melting temperature of plate material and causing it to melt and rise up through the mantle and sometimes through the crust to erupt as a volcano. But that generally doesn't come until college. So I took it out of here because I just don't believe that people are really going to do that.
Okay, thanks for your perspective. The piece here, and what we have here is, again, not necessarily you're an expert on students with special needs, but Jackie asks, I think, a good question of how would you explain modifications for special needs students on these standards? What would you suggest?
I am really not prepared to answer that, so hopefully someone else here, maybe in the discussion, can weigh in. I apologize. I can make something up.
Problem, and I think so much depends on. Yeah, so much depends on what the particular special needs of the student are. I think the approach of the standards as progression lets you kind of look back in the progression and think of some things to do is one piece I would think of myself, but it really depends upon what the needs of the student are. So I'm trying to see here if we've caught up. I think I've hit all the questions that we've got out here right now. Why don't we go on to our next section? People can still post some questions here, and we'll get to another question break in a little bit.
Okay, great, and thanks for responding to the poll. It's very, very interesting, very useful to know. Okay, so I'm going to dive in here to the next big component idea, and that's Earth's material and systems. And the framework describes basically three big ideas that comprise this component idea. And that is that all Earth processes are a result of cycling of matter and energy within and among Earth systems. These processes consist of interacting subsystems within the Earth system, the geosphere, hydrosphere, atmosphere, and biosphere. And the Earth systems are dynamic and continually react to changing influences, including human activities. So I think the connection between this component idea and the overarching conceptual framework that I presented in the beginning is going to be very clear. So this ESS2A is really a component idea that kind of ties all of the other ones together. And so let's see how that plays out in K-12. So in elementary school, we start out introducing students to relationships between those four Earth subsystems. So ways that the atmosphere interacts with the geosphere, and the geosphere influences the atmosphere, etc. We also start thinking specifically about interactions between the atmosphere, hydrosphere, and geosphere. So erosion and deposition shape the Earth's surface. The specific set of interactions that are highlighted here. Elsewhere in elementary school, we see that students are starting to think about human activities and the impact that they have on each of these subsystems. So you can make connections to that. We're also thinking about time scales. So when you talk about interactions of subsystems, you can bring in the relevant time scale there. In middle school, they're starting to put together the a kind of mental model of these four subsystems interacting. So learning that energy from the sun and from Earth's interior drive a global cycling pattern energy. So they're taking these sets of relationships that they started putting together in elementary school, and they're adding this layer of complexity of looking at them not as a whole bunch of individual relationships, but tying them all together as ways that energy drives cycling of matter and energy through the Earth system. So all of these are not separate concepts. They all have this unifying theme of cycling of matter and energy. And as matter and energy cycle through these systems, a byproduct is that the surface of the Earth is changed. Elsewhere in middle school, we're building on the elementary school, they're learning human activities and major impacts on subsystems, and in middle school, they're learning about the dependence of humans on these interactions. So thinking about natural resources and how interactions of Earth systems distribute natural resources, and that's actually hugely important for human history and current events. In high school, they add a whole another layer of complexity. So in middle school, they're kind of building this basic model of the Earth system and relationships between the different subsystems and how energy and matter flow through them. In high school, there's a sort of real-world aspect of dynamic global systems interactions result in feedback effects. So they're learning that not all interactions are equal. So a small change in one part of the system may be reflected as a large change in another part, or an increase in one part, decrease in another part. So they're starting to add this kind of real world aspect to this general model that they're learning in middle school. They're also learning about thermal convection as the main driver of matter and energy cycling through the Earth. So convection is a big part of plate tectonics, so we'll hopefully get to that later. Elsewhere in high school, they're starting to think about cyclical changes in the solar system, so that you can bring that into the dynamic global system, regular long-term changes in the global system. They're also learning about, they're going into depth with dynamic relationships between human activities, the biosphere, and atmosphere. And so they're going to have a sort of detailed understanding of those sets of relationships that you can draw on as they start to work through this really complex global system. So how has Earth's material systems been approached in the past? So as usual, it can be summarized in diagrams that just show absolutely everything. And even when I look at this, it just, I have to really, really read into this to put together what the point is. Now, when I look to the research and I look to what other people have done that can help us do something better with this topic, I come up a little bit short. And this is a very frustrating part of the presentation for me, because as I think it was clear from the introduction to our systems, this is really a very central component of the entire Earth systems topic. Yet we know very little about how to do it well. In fact, I would argue that although we've seen statements about the interactions between the four subsystems in standards before, I haven't seen them really addressed very thoroughly before. It's usually just sort of one among many standards that often doesn't get a lot of attention, as opposed to the central theme that holds together all of our systems, all of learning about the different systems. So one thing we know, not from our science, but mostly from business, is that students, actually people, have a very hard time with systems, all systems. We also know that there is very little research on students' ideas around using, teaching about interacting systems, subsystems within the Earth system. That we can see sort of a reflection of the fact that this hasn't been taken very seriously in the past, and that there's not a lot of development in this area that we can refer to. There are some people who have been working in this area, and so I'm going to introduce you to some resources that that I think will be really helpful. So there are some people who have really been thinking about what it means to talk about systems with students. So we talk about, like, NGSS put systems thinking at the forefront. What does that mean? I'm not going to get into this, but if you're interested in this work, and this is just a brief excerpt of their sort of theoretical reasoning around what it means to do system thinking, I can help you find this resource that I cited at the bottom. The same set of authors found a lot of success using concept mapping with helping students to build complex systems. So we have two concept maps for the same students, learning about the water cycle. If you're not familiar with concept maps or using them in the classroom, there are a lot of resources out there, and I'm going to let you find those that can help you then if you need help with that. But these people have found that concept maps can be particularly helpful in really seeing into students' minds and getting an idea of the connections they're making, and where to help them where they're doing well. And you can see this one student and the dramatic increase in complexity in their mental model of the water cycle. Another resource I'd like to point you toward is CERC's Earth Lab. CERC is a website out of Carleton. The link is below. And I was very pleased to find that they did a lot of scouring to try to find something useful to share with you for this very, very, very important idea. And they developed a freely available entire unit that couldn't be better aligned to Earth systems in NGSS. And regardless of what grade band you teach, I recommend looking at this website and at least adapting what they have for your needs. And just to give you an idea, they have students use the local study sites, which is right outside their school, and kind of deconstruct it into sets of interactions and create diagrams that sort of layer on ways matter and energy are cycling through that site. And they get students to progressively think broader and broader and broader, and place their site into a broader regional and then global context using graphs and data, and all of these resources like the GLOBE data set are available as links through their website. So I point you to them and offer that as the most useful thing that I can share with you about this really important topic. I really hope that given that NGSS has made the interaction of the four Earth subsystems and the way matter and energy cycles through them and shapes the surface of the Earth so central in Earth science, I really hope to see it as an area of a huge amount of development in the future. I seem to be stuck.
I think we just had a little delay.
Jill, I'll go ahead and get the slide
okay, thank you.
For you. It'll take me just a moment here, so if you can just delve a little deeper into what we've got, I'll be with you shortly.
Okay, well the next slide is really asking for questions. So this is a good time to solicit questions from you. I also have, I believe, another poll there, but we'll just stop for the questions.
That's great. Thanks, Jill. So I'm going to start with a question I've got in terms of your approach in thinking about the complexity of dealing with different things as a system and looking at what you did with the water cycle. Would you suggest that similar to the way you approach the water cycle or the standards are approaching it as well, working on different elements and the connections between elements before you try to take on the entire systems approach of it?
Yes, I definitely would. And if once you have a sense of what's in each of these 5 components of Earth systems in NGSS, you can see that Earth systems is ESS2A, and B through E each address or kind of bring one of the subsystems to the forefront. A brings all of them together. And so it took a while for me to kind of see the pattern here, but I think it was helpful for me to see that that they have kind of broken the topic into the 4 subsystems and the 5th idea being bringing them all together, and I'd probably rearrange the order from what they did. So as you said, address each of the 4 subsystems on their own, and then try to pull them together with the topic Earth system.
That
for the
makes
poll,
some sense,
as you can see, I was very curious.
We benefit from your...
Go ahead.
Okay, go ahead, Jill.
Yes, so you can see I'm really curious to hear, without a ton of resources and probably not a lot of history addressing this kind of topic, how comfortable you are feeling teaching about Earth in terms of 4 interacting subsystems.
And that's great because that ties into what the piece you're saying here. And I think we're all benefiting from your insight of having looked at the standards pretty closely in your previous experiences in curriculum. I like we've got a question here. Do you have some recommendations about where to get some research-based curriculum resources for these core ideas, particularly at the middle school and high school level? Is the question Dave has for you.
For this specific core idea,
yes.
Well, I did look a lot. I'm sure that there are more out there, and I really don't know how much research is involved with CERCs. But I'm sorry, I can't be very helpful with this topic. I looked a lot, I saw some, I chose not to include them because I didn't think that they really hit the point of this topic that NGSS is making. Whereas as CERCs,
I think the point you're making is a good point here. Is that NGSS is taking a very different approach to earth science than it had been done in the past, and is going to necessitate the need for new resources, new curricula, in terms of all of we do here.
I saw that.
So Jackie, I think, has a great question here. I think we all sort of struggle with this. How do we cover it all? How would you deal with that? As someone who's struggling to fit this into your to cover everything you'd like to in our presentation today, maybe I think it'd be a great point about how you might approach the topic.
That's a great question, and I knew people were going to be thinking of that as I completely ran out of time even talking about all of these ideas. And I'm trying to make the point that in a lot of ways, even though they're thinking bigger and they're asking us to think bigger in NGSS, they're really asking us to zero in on really basic, simple relationships that allow us to think bigger. And so for example, with the water cycle, rather than focusing on all of, the details of the water cycle we often get bogged down in, it's really just focusing on a pretty straightforward relationship between sunlight, the surface of the earth, and air, and how water is transferred between them, among them. And so even though it's the same substance and it's a little different perspective, in a lot of ways, it's much simpler.
Well, one thing I'm liking from what you're talking about here, as you've got all these different systems, there's some aspects with your unifying idea that you would sort of attack in similar ways, and that I would think, well, the truth will be in the telling, or in the teaching, I should say, that if students really start going in depth with some of these concepts and they get one of these systems and understand it well, that process should make it easier for them to understand other types of systems going along and getting to that idea of what systems thinking is really about, which is, I think, one of the really powerful things in the standards. Great. So why don't we move on to your next
okay, great. And I'm glad to see that
from there.
Forward button is working. Okay, plate tectonics. So the third component idea I'm going to talk about is plate tectonics and large-scale systems interactions. And as the framework really describes 4 big ideas for plate tectonics, including the movement of plates is supported by multiple lines of evidence, and that's going to look, thankfully, very familiar to a lot of you as an expectation. The movement of tectonic plates is driven by the release of energy from the Earth's interior and gravity pulling the plates toward the interior. Convection inside the Earth results in plates pushing together, pulling apart, creating and destroying ocean basins, carrying continents, causing earthquakes and volcanoes, forming mountain ranges and plateaus. Okay, so these two together, again, describe a pretty familiar topic, a way to talk about plate tectonics, again, from a slightly different perspective. So we're talking about all of these surface features that we always talk about, but rather than forefronting those, we're forefronting convection. And the movement inside the Earth's interior, the cycling of matter and energy through the Earth's interior, a byproduct of that cycling is the formation of the movement of the plates above the convecting mantle, and a byproduct of the moving plates are these surface features. So again, same substance, a slightly different perspective. And finally, tectonic activity has shaped and reshaped the Earth's surface in the past, and these processes continue today. Again, familiar. So, plate tectonics and NGSS. Elementary school. Maps show shapes and locations of surface features on the Earth. So, observational of these surface features using maps. Very similar to at our Earth science elementary school standards. Elsewhere in Earth science, they're learning about rock formations, recording changes over time, so you can draw on that. And what they're thinking about natural hazards, you can make connections to these surface features and what they're learning about with natural hazards. Middle school. Maps show a history of plate motion. Again, observational on the surface of the Earth. Now they're thinking about the relationship between plate motion and these surface features, but they are not learning about a cause of plate motion. So it's still using maps to make observations about features on the surface of the Earth, including evidence for movement. So that's probably a little different from how you've seen plate tectonics in the past. It really limits what's going on in middle school. High school, there's a lot. Mantle convection moves plates across the surface of the Earth and creates a pattern of geologic features. So again, this motion within the mantle results in the movement of plates above the mantle, and a byproduct of that is the pattern of geologic features. They're also looking at mantle convection itself. So convection is driven by energy released from the Earth's interior and from plates being pulled by gravity. I had to remove all the slides I had about convection because it was taking up a lot of time. We could probably dedicate an entire webinar on addressing convection in Earth science. It's really, really tough, and I wish I had time to talk about some of the considerations that we have to make when addressing convection. Just to point out a couple things to keep in mind in physical science, their understanding of radioactive decay, which is, as you can see, one of the drivers of a convection cell. Spontaneous radioactive decay follows characteristic exponential law. That's what they're getting from physical science. So you need to build from there. They're going to need a pretty good introduction to a connection between what they got in this sort of generalized introduction to radioactive decay and what they'll need in the real, how it plays out in the real world. And you can also draw on what they're learning about for conservation of energy. As you probably already do, you also want to make connections to they're thinking about convection in the atmosphere and ocean. And although I cut everything about convection, I'm going to add back in my plug for you listening to Jeff Nordine's NSTA webinar on energy in NGSS. And I no longer have the link up here for you, but I think all of you know where to find it. I really recommend that everyone who's teaching Earth science does a little revisiting of their understanding of energy, as I always have to do. And Jeff did a really nice overview of energy in general and energy in NGSS. And considering how central it is in Earth science, it's really worthwhile just watching the webinar if you haven't already. Okay, so plate tectonics, how is it typically approached? Well, again, we always see these diagrams that just sort of show everything in one diagram, and it's hard to kind of parse out what's really important to get out of it. So students come out of learning about plate tectonics really not having any idea the relationship between these big abstract concepts and the world they're standing on. They can talk about earthquakes and volcanoes and plate tectonics as the cause, etc. But when you ask them what plates are, they think they're at the core and that they never are visible at the surface of the earth. And so it really brings this question to the forefront of what on earth do they think the relationship is between these abstract concepts and the world they see. And so a diagram that I think addresses the concepts in NGSS a little better really zeroes in on the relationship between convection cells and the motion of the plate above. So it really zeroes in on, as you can see, the motion of these two convection cells and the these two plates pulling apart. So in NGSS, again, convection is the sort of centerpiece, and the motion of the plates above it is a byproduct. If you use these still, very abstract diagram, one piece of advice is that whenever you use an abstract diagram like this, you pair it with other representations so students can try to piece together some kind of understanding of what they're looking at. We often use these block diagrams. They're really confusing to students, but they're also really useful if you can help them understand what they're looking at. When you use them, always pair them with some image of what you're talking about in the real world. It's the best advice I can give you. We have lots of ways of imaging these big things I'm talking about in the real world. Example, subduction zone. We often talk about the Mid-Atlantic Ridge as this huge surface feature, but we also have pictures of how it, like photographs of it up close. And we compare these images to start helping students make connections between these concepts that just seem totally unrelated, so the world they're standing on, to help them merge these two understandings. I also recommend when you are always going to use the ring of fire, but there are more and less useful representations. This is actually an animation. This is still of it. And we can bring in time. We can bring in current events. So this animates the earthquakes that happened today, earthquakes that happened yesterday, this past 2 weeks. And it shows that the entire ring of fire can be shown, every part of the plate can be shown as earthquakes just from the past 5 years. So you can add an extra layer on top of the ring of fire. So you can see now I'm racing because I really want to get through the rest. So I quickly want to throw an opportunity out there to ask questions and to give me a sense of how you feel about addressing convection as a transfer of matter and energy.
So we'll give everybody just a moment or two to put their feedback up on this one, Jill, and maybe take 1 or 2 quick questions. We'll see if any come in the next little bit here, but if not, we definitely will have some time at the end to get to final questions.
And Dave has mentioned here, it's great how we've got people suggesting resources and sharing what they've found at different points. I'll give a little shout out that NSTA actually is working on a website that will provide a way to view the standards and for educators to share resources with each other or to point to resources they found that are targeting particular ideas. So we will be in 2014 trying to deliver something like that for you as a place to work with. Looks like we've got thanks to your work, Jill, people overall are feeling kind of pretty comfortable about these pieces here. Let's see here. I'm just trying to skim through here. Mary asked an interesting question about whether convection is a term that can be used at the elementary level, 4th or 5th grade.
I wouldn't recommend it. I would, I really suggest referring to the energy topic in NGSS and getting a sense for their recommendations for K through 12 for where, when different concepts should be introduced. And I tend to agree with their recommendations that in terms of earth science, you can see in elementary school there is a heavy focus on things that students can observe about the surface of the earth. They're very math focused, and so the decision to not include processes that are more abstract was very conscious, and I personally agree with it.
Great, thanks, Jill. I'm going to take a crack here at Jackie's question about the relationship between NGSS and the Common Core and math and social studies. And the writers of NGSS very much were looking at what was expected in Common Core Math, Common Core Common Core ELA, English Language Arts. In fact, it's probably NGSS is the set of standards that is most explicitly connected to math standards that exist. I'm not aware of any of the others that are. And you can find at the bottom of every page in the standards links or connections to particular statements in the Common Core, both for math and ELA, that are appropriate, as well as I think a number of you have seen the Venn diagram that compares practices in math, English language arts, and science, and how those come together. And so with that, I think we'll pass this up back to Jill to go through her last piece.
Okay. So next we have my pet topic, weather and climate. So the big ideas that the framework asks for weather and climate focus on, first, both weather and climate are shaped by complex interactions among components of the Earth system over a range of timescales, probably pretty familiar. The sun warms the surface of the Earth, trace gases in the atmosphere absorb energy radiating from the Earth, also pretty familiar. Ocean and atmospheric circulation redistribute energy globally. Changes to Earth system can change the climate, feedback loops amplify or maintain stability. Okay, so how does this play out K through 12? Elementary school, they're really just looking at the difference between weather and climate. Very important for them to get a bit strong grounding in that, and making observations of phenomena. Elsewhere in elementary school, they're looking at natural hazards, including weather, so you can make connections to that. And they're also learning that sunlight warms the surface of the Earth, so that will be really important to prepare them for middle school. Middle school, they're starting to observe regional and global climate patterns, and they're putting together the basic components of the global weather and climate system. So starting to think about the relationship between energy from the sun, surface of the Earth, temperature of the air, and that basic set of relationships and how that drives weather and climate. High school. Global climate system is a function of radiation from the sun redistributed among the ocean, atmosphere, land system, and radiated into space. And so while in middle school they're piecing together these basic relationships, in high school they're starting to reflect on those basic relationships as a mode of transfer and transformation of energy across the surface of the Earth and radiated back into space. So again, connections in middle school, they're also learning about human activities and how they impact each of the elements of the climate system. And of course, water cycle, movement of water in the atmosphere, driving local weather. And in high school, they're learning about cyclical changes in the Earth's orbit and factors that can impact the global climate system outside of this basic relationship between the sun, surface of the earth, and air. So volcanism and changes in vegetation and human activity, etc. Typically, we see a diagram like this that I'd be really happy to never see again in K-12. And my problem with this is there's so much information here that the point, I think, is really obscured. And we know that students come out of this topic with a huge number of misconceptions that imply that they are really confused about the role of energy in the Earth system. And what I would love, even though there's some terrible things about this diagram, number one, the relative size of the sun and Earth, but it zeroes in on this very basic relationship that sunlight transfers energy to the surface of the Earth of the Earth transfers energy to the atmosphere, some absorbed by the atmosphere, some radiated back into space. We can add some complexity here and talk about, well, there are different things covering the surface of the Earth, and that impacts how much energy absorbed and reflected and radiated, and there are different varying composition of the atmosphere, and that can influence how much energy is absorbed and radiated into the atmosphere. But we're still really zeroing in just on this very simple relationship, but it's key to understanding everything about the weather and climate system in a way that that diagram that shows all of the arrows and percentages kind of obscures. Similar to other topics, once we understand this very basic relationships, we can start. This is another animation that shows sea surface temperature and circulation of ocean across the surface of the Earth. The link is below. And we can bring in data like this, and once students have that very simple, basic set of relationships, they can use them to start making connections to the how water in the ocean moves thermal energy from place to place, how that impacts weather in different places, how that impacts the hydrosphere in different places, how it impacts the biosphere in different places. We can use that very basic understanding to have them use this as a platform to develop models, plan investigations, construct explanations, etc. So before I move on, this is in a lot of ways, weather and climate is, again, based on the same substance as you're familiar with, and it's just putting the flow of matter and energy through the system in the forefront instead of many of the other details that we ask students to memorize about weather and climate, and saying that if they have a basic understanding about how energy moves from the sun to the surface of the Earth, through the atmosphere, through the ocean, that then they're prepared to build a model of weather and climate that can then help them, that contributes to a understanding of how the role that weather and climate plays in the larger Earth system.
We seem to have lost audio for Jill for a second here.
And I'm going to
just
move directly into this last component idea very, very quickly. This is the overview portion of the presentation. Biogeology in the framework is described. Biology in the framework is pretty substantial, and I think all of us will breathe a sigh of relief, even though I have a PhD in in this area. I was rather relieved to see that ultimately, though there are big ideas in the framework asking students to understand the relationship between evolution of life and how it impacted the history of the Earth. If you look at the standards, almost all of it was peeled out. So this was going to be a pretty new set of expectations that in the end, the writers of NGSS decided that there was just too much, in the whole topic, and biogeology was the area that got the most cutting. So we still have in elementary school this idea of living things affect the places they live, and we still have this idea in high school that dynamic feedbacks between Earth's biological systems and physical systems affect both systems. And I think it's pretty clear how these are just examples of the interaction between the biosphere and the other spheres in a way that that we've actually touched on in a lot of other areas already. So it's in some ways already kind of built into the topic. And that's really my overview of Earth systems. And so had we the time, and maybe it will be something we'll be able to reuse it later, but I'd love to hear at some point how you as classroom teachers, most of you I expect, what kind of, how you might capture the goals of NGSS as I did. Would you change it for communicating to other classroom teachers? How would you change it? What kind of framework do you think would be really helpful?
I think a great piece here.
But that is the end of my part of the presentation.
You can start to write down if they want to some of their ideas in the chat window. I'm going to go through just to take a little bit here to let them see what some of the resources at NSTA are. Then we'll give people a chance to fill out their evaluations, and we can continue the conversation a little bit after that. After the evaluations have been completed, have a sort of a more relaxed conversation. So let's jump here a second. You hopefully are aware of the website for the standards, nextgenscience.org, and NSTA's website dedicated to standards, nsta.org/NGSS. Also, be aware that we've got a discussion forum in the Learning Center specifically devoted to NGSS and a member-only listserv on NGSS. We've got one more in our Earth Science section, Earth and Human Activity, which will be 2 weeks from tonight. We've got, I've suddenly blanked Susan Burr from Ceres and UC Boulder to come and speak, and we have a full slate coming. I think January 28th is the first of our life science pieces, and we'll go through the spring and cover engineering design as well. We've got plenty of archives of our previous web seminars and the practices, cross-cutting concepts, and the disciplinary core ideas, and also a number of journal articles in our different journals devoted to NGSS. An online short course we've got coming up in December featuring Picture Perfect, really focusing at the elementary level. Emily Morgan, author of Picture Perfect, will be doing a 3-session web seminar, and you can see the places where you can link up to that. So we have also some new books from the NSTA Press Bookstore. If you want the standards in print, you can get them there. We've talked about the framework. NSTA also has Reader's Guide to both the framework and the NGSS, which can be sort of good companions to those books, give you some sense of it. And just about a month ago, just released Translating NGSS for Classroom Instruction by Roger Bybee, one of the NGSS writers, and really tries to say how can we go about taking the standards and breaking them down and going through and teaching. I hope some of you are aware we've got an app for NGSS developed by Mastery Connect. And you can get that NGSS on either your tablet or your smartphone, because you always want to have the standards at your fingertips. Yeah, I know I'm always looking them up. Conferences, I'll be in Denver in a couple weeks at our area conference, and our national conference is coming up in Boston. Hope to see you at one of those two or both. And with that, I just really want to thank Jill, who's really given us a great way of trying to tackle what is, as we all acknowledge, is a really massive area. The earth sciences are really far more featured in NGSS than they are in some of the other in previous standards. They've really come into their own, and that leaves a lot of ground for us to cover in our classrooms. And Jill, thank you for sharing some insights about this. And so, Bryn, I'll turn things over to you.
Thanks so much, Ted. Wanted to thank you as well as Jill for presenting today's content. And we also wanted to thank the Carnegie Corporation of New York for sponsoring today's web seminar. We wanted to thank the administration of NSTA for their support for web seminars. And I also did want to remind everyone that we do have a web seminar collection that has not only the recording of today's presentation as soon as we finish, as well as the slides, but also some great related materials. We have journal articles. Some of those that Ted mentioned are right there in the collection, as well as our science objects and SciPacks. I saw Dwayne and Erica mentioning in the chat window that they've tried the SciPacks and they really like those opportunities. Really do encourage everybody to check those out as well, and they're available for you right there at the link that I've just put into our chat window. And to close up, I wanted to remind everyone about what's coming up on the web seminar calendar. This week we've got a continuation of our NASA Explorer School series with Heat, Temperature, and Energy Messenger Cooling with Sun Shades on the 20th. On the 21st, we'll be looking at linear equations, NASA Connect, breaking barriers. And then next week on the 26th, electromagnetic spectrum, remote sensing ices on Mars. And you can register by going to learningcenter.nsta.org/webseminars. Thank you, everybody, for your participation today, and we look forward to seeing you again on another web seminar.